Hi, everybody. Welcome to our next seminar for XFC 2024. Our previous seminar was given by the same speaker as today, Dr. Barnabas Bede from Digipen Institute. The previous seminar was all about gradient-based optimization of fuzzy systems and gradient-based learning, including backpropagation. And this is sort of an extension of that, as he's going to get into reinforcement learning techniques with fuzzy systems, which are gradient-based. Dr. Bede is a researcher at Digipen Institute, mainly in the areas of fuzzy logic and mathematics. He's also heavily involved in NAFIPS, the North American Fuzzy Information Processing Society. As always, this talk is being recorded and will be uploaded to YouTube. And if anybody on the student teams has questions for Dr. Bede, you can put them in Slack and we'll relay them as needed. But with that, I'll turn it over to Dr. Bede to talk about reinforcement learning.
Yeah, thank you very much for the introduction. I just wanted to make a quick advertisement about next year's NAFIPS conference. Yes, so let me do a quick ad about that. So its web page is online, NAFIPS 2024, digipen.edu, where we will still be working on submission and other things, but we have a nice location, as you can see. Yes, think about attending. Yeah, maybe we can put in the chat somewhere on the recording that link to the web page.
Yeah,
all right.
I'll put it in both the chat and the YouTube video.
Yeah, thank you, Tim. So let's see. So we will talk about reinforcement learning with fuzzy systems. Yes. Can you see my slides?
Yep, looks good.
They are on the side, but on the left side of the screen, but yeah. It's going to work this way. So reinforcement learning with fuzzy systems. Basically, well, we will start with going over fuzzy systems that we did yesterday. However, we will focus more on reinforcement learning, so we won't go into details on those. So fuzzy system, as we already have been considering, it's of the form fuzzy is based on fuzzy rules, which are of the form if antecedent or antecedents, if there are multiple ones, then consequence. So sorry, I don't know how it jumped to the very end. The calculation of the Mamdani based, so this is the Mamdani fuzzy system, and the calculation of the Mamdani output is based on input firing levels of each rule, its intersection with the corresponding outputs, and taking the center of gravity of the output. Yes, so as we could see last talk also, we had three firing levels that resulted in a shape of this kind for the output of the system, and then the center of gravity of that is basically the average x coordinate based on weighted by weight. Yes, the Takagi-Sugeno systems are a lot better for learning. They are of the form if x is ai, then z is wi, and their output is a simple weighted average of the individual rule outputs. Yes, of course, this wi could be also of the form ax plus bi, which could be partial linear. So some of the today's outputs were constant, some of them were linear, so we experimented with both of them. So now let's focus on reinforcement learning, which is the main topic for today. Yes. So first, reinforcement learning without fuzzy. So what is reinforcement learning? Sorry. Sorry, resizing has been automatic somehow. So reinforcement learning is a paradigm in training various machine learning algorithms, where an agent observes the environment. This observer is here to observe the environment and gets a state from the environment. Well, we can observe what state we are in and obtains a reward from the environment. Then, based on the state and reward, we make an action on the environment, and then we get new reward and new state, and we repeat this process. And the goal in reinforcement learning is to maximize the reward that we get, basically. Yes. So this is a simplified version of the previous picture. So we have a state st and reward rt at time t. Yes. The agent observes these from the environment. And then, based on those, takes action AT, T being the time step, and then increases time step and does this action in the environment, and the action returns, the action influences the environment, changes it, and the environment responds with a new state, will be in a different state, and the new reward, RT plus 1 and ST plus 1. So basically, some terminology related to reinforcement learning. Capital S is the set of states, the total set of all the possible states in the given problem. Yes. So what problems can we look at here? Typical environment is a maze. Yes, where you want to find, so there is a mouse in a maze. Yes. And wants to find the cheese, but wants to avoid the cat. Yes. So how to do that? Basically, the states in the environment correspond to different positions of the three, three entities. ST is the state at time in the moment t. A is a set of actions that I can do. For example, for a mouse, it could go up, down, left, right. Yes, any direction. Of course, here it would hit a wall, but in general, it could go different directions. Yes. So those are the set of actions that we take. Pi is a policy. Policy assigns to every state an action to be followed. Yes. So we know that we are here, for example. The mouse is already here. It makes sense to just do the step to get directly to the cheese. So that's a policy, basically, which would show which way can I reach the cheese with the mouse. Yes. Reward, R of S, is the immediate reward in state S. Typically, we assign a reward of +1, a positive reward to something good, and a negative reward to something bad that is about to happen to our agent. Yes. Coming up with a good reward function is a problem in reinforcement learning, and getting a good reward basically is called reward shaping. So you get the different ways and training, and different ways of rewarding the agent will give you different results and different speed of training also, or different stability. So you want speed and stability at the same time, which are also, of course, impossible to achieve at the same time. P of S prime SA. So we are in state S, we take action A, and we end up in state S prime. That's not always straightforward. So we might have, for example, this mouse is not good at listening. So we tell him to go this way up, but with a certain probability, this mouse may just go left or right or down without yeah, so they could go with a transition probability to different states. Even though the policy doesn't tell you to go this way or that way, you could have a different transition probability you could get in different states. Well, in many situations, we have a typical, well, the agent does what we make him to do. So in that case, these probabilities are non-zero. But imagine this also applies to web search. So for example, Google's algorithm returns 10 best 10 best results for a Google search, and basically users are supposed to click on the first one. No, that's what Google tells you. Do you always click on the first one? No, you might have a non-zero probability to click on the second. Well, considerable probability to click on the second, third, so on and so forth web page. In that case, you are the agent and you are clicking on web pages and you want to find the information, and your reward is if you find the information. So yeah, value function. Value function is the expected total reward. So let's say that our environment is a little more complicated. So there is a big cheese here, but there is a small cheese over here. But there is a negative reward here, being basically showing you that you should very quickly get to the cheese if possible. So the total reward, basically, I'm taking the action S0. Sorry, I'm in state S0, and I'm taking the actions S1, S2, S3, so on and so forth. I get a reward for S0. Then I get a future discounted reward for S1. Yes. So value function will basically add all the total possible expected rewards with a discount factor for the future rewards. So of course, immediate reward is better than future reward, but future big reward could be better than immediate small reward. Yes. Combining these ideas, you can come up with such a function. Gamma is a discount factor, which is typically less than 1, 0.9, or things like that. Okay, so this is the typical environment that we talked about. So mouse, cheese, cat, and each agent can take different. So the agent can take different actions in each state. Yes. So we have basically 4 possible actions. If it goes, hits the wall, it stays put. If it goes left or right, yeah, we can see which way to go. So basically, reinforcement learning tries to lead the agent to the reward. Yeah, now, well, it's kind of obvious that we should go this way to avoid the cat with any means, but you know, an agent initially has no idea how this looks like, so they could just go random and explore randomly the environment. After a while, they could record what was the reward if I went this way, what happened if I go this way. So all this together lead to the value function. The value function will determine what is the value of each cell. For example, this will have a value of 0.75 because I can very quickly get here. Okay, it's not just, this is just a made up number, so I'm not sure if that's correct. Yeah, so the expected future reward starting from this cell is going to be recorded here. That's going to be the value function. And let's suppose that we have somewhat like this. And this way we have different values. So what do I do basically when I'm following my advice? Well, let's say that the mouse is good at following directions. Then it would go this way to reach the cheese based on the value function, the immediately best value function I can select, and that's going to give me the best policy. Yes. So policy is basically a set of arrows that I can put on the graph that if I go this way, here I should probably go, well, and here there will be a non-zero reward here. Yeah, so here probably this way, this is negative 0.5 because this could end up there, yes. So here's the deal. I can fill up this all this thing with arrows. Basically, the arrows represent my policy. I can calculate these expected probabilities, expected values, and those will be my value function. Yes. So here's Bellman's equation. Bellman's equation connects all these together. Yes, reward, probabilities, and value function. And the Bellman's equation is at the heart of all reinforcement learning algorithms. So the agent receives rewards S taking action A. Yes, VS, the value function, can be computed by the following formula. You immediately get the reward S that is in the current state. Yes, so you basically get the actual reward that is here, plus gamma, this is the discount factor, times you sum up all the possible next states from the current state. Yes, so S prime is the next possibilities that you can get. Yes, next possible states. And each of those will have their own value already calculated. Let's say VS prime. Of course, this is if I know already VS prime, I can calculate completely easily VS. But VS, basically you can see that this is an iterative procedure over here. Nevertheless, this is a linear system of linear equations. Yes, if you look at it, these are the variables in this system, and the dependence is a linear one. So this is a large system of linear equations, typically, which, well, could be solved if we have complete knowledge of the system. But typically, the number of equations in these is actually infinity. Yes, infinitely many states are possible in a problem, then you have infinitely many equations, or could be different sizes based on difficulty levels of a game. For example, for chess, the possible states are each possible board. Yes, those are many. Yes. Okay, so how do you actually compute this with the Bellman's equation? You assume VS prime some random value, typically or 0 initially, and then you iterate on the equation, and this current reward updates the value to a better estimate on what's next. Yes, it's somewhat like Jacobi iterations or Gauss-Seidel iterations, where you iterate in the linear system, basically to calculate the next best approximate solution. Yes. All right. Now, Bellman's equation doesn't give you the best choice. It just gives you all the possible choices. But Bellman's optimality equation says that if you choose here the best action, then you will get the best value out of your game, basically. So V star is the best optimal value function. V star is the optimal value function. Yes. So it means that So what means this here? I take the best possible action that that can give me the best possible outcome from the current state. Yes. So this Bellman's optimal equation says that V star, the optimal value function, is basically obtained when I take really the best action. Yes. Just the average value function is just if I take any action in any direction, I can calculate those. Okay, so let's look at temporal difference learning now. So how this comes together with gradient, how this combines with gradient descent. So last, I almost said class. It's not a class talk. Well, yeah, it looks like I'm teaching plenty of classes, so I assume I'm teaching, no? So TD, temporal difference learning, is a gradient-based reinforcement learning method. So what do we want? Basically, we want to maximize VS because VS is the optimal value. Yes. So what do we do? This is a maximization problem, and we saw that gradient is in the direction of going towards the maximum value. Yes. And typically we did gradient descent to minimize error. But now for value, we want to maximize it. So how do we do that? We calculate the gradient of the value function, and we update the value based on that with some learning rate eta here. Yes. Now, what is S plus ds? This is basically your next value function. Yes. Which then you can approximate as R of S prime plus gamma times V of S prime. Yes. So you get the reward from your next action. Yes, that's V of S prime, basically an approximation for, because you get the reward plus a discounted future reward of V of S prime. So this is basically V of S plus delta S plus ds. And well, these are just constants, eta and ds, so we combine them into a parameter alpha of the system. Yes. Now Q learning. So you have many concepts that you could explore here. There is value iteration algorithm. So value iteration would actually iterate on these type of equations and get best reward. Temporal difference learning basically does update V of S based on this and then gets the best policy out of it. So there are many ways to do learning. I just recall those that we want to use. So the next one that we worked with is Q learning. Q learning optimizes the action value function. Yes, action value function is called Q. That Q comes from quality, I suppose. So action value function is the expected maximum reward obtained from a state S. Yes. If we take action A. Yes. So that's basically the Q learning. So what is the difference between value function and Q learning? Because it looks like this, expected maximum reward. Is that I take the action. Yes. So basically when I have this grid problem, yes, and let's say I'm here, I can take any action and I'm going to have 4 Q values. Q of S for this state S, I'm going to have 4 Q values, SA1, let's say the action to go up, Q of S going down, Q of S taking right, Q of S taking left. Yes. So basically we have a action value function for each action and each state. So this is a matrix of large matrix, basically where you have different different action value functions in different actions taken. Yes. Now Q-learning with temporal difference combined. Basically, again, you want to maximize Q of SA. This time you want to maximize Q of SA. And well, same formula that we had for the V. Yeah, so Q of SA plus alpha times the actual reward plus Q of gamma times Q minus Q. So this is basically a temporal difference with respect to which you can update your Q values. Yes. When updating the parameters of the system in reinforcement learning, so Q values we update, but what is basically governing our choice? Typically, we will have a neural network that will predict the Q values. So the big idea of Q learning and the deep Q learning in special is basically we have a neural network that predicts the Q value of each action, and we take the best possible action because I know all of them and I'm going to take the best one. So that neural network will have parameters. How do we update parameters of the network? Yeah, well, basically, we update them based on this equation. This is the temporal difference here. Yes, this is the temporal difference part. And when you update, yes, so basically this is Q of S new minus Q of S. So you basically subtract these two, and that's going to be your new, the difference between old and new. Yes, that basically is backpropagated through the network in the form of the gradient. Yes, the partial derivative of Q with respect to Wi. So here you need to basically do backpropagation on the network to basically update all the weights Wi in the Q learning case. Okay, but now we said that we will take the optimal action. So when maximizing Q, I can also get a little trick here, add it to my system. I already take here the best action so that I get the most reward possible, not the best Q value possible. And well, you get the current reward no matter what. But I get the most possible future reward basically here by maximizing the best, taking the best action from S prime. Assuming that I know already this one, I can then optimize my parameters of the system based on this. So this optimization problem basically breaks down the problem into two parts. We will have a target network. So this will be the target part. So we will have a target network, and the current network will try to reach the target network. Why is that? Because Q learning, I forgot to tell you, is really unstable. So many times the system will chase its own tail. Yes, we'll improve Q because this is bigger, but then that moves away. So I'm chasing it again, and yeah, so it goes in a circle around different non-optimal values. To get that somehow stabilized, you can work with a target network. The target network basically is, yeah, so you basically have two versions of the network that outputs the Q value. One that is the target network and your current network. So you fix the target network for a couple of steps, yes, so that you allow the current network to optimize to get that best possible action from the ones that have already been done, yes. So maximizing that looks like this. We calculate the target from the target network. So here you use the target network. So here you use target network. And here you use the basically the actual network, or well, don't know. because the target network was actual at some point. So basically that's how you get the target network. You fix it and then run the current network, I'm just going to call it current network until it gets closer to the target. And the target, because of this maximum value here, is taking the best action among those available. So it's going to be better than what I have in the current one. So how this works with Takagi-Sugeno-Kang systems. So yeah, and basically here we get into the TSK fuzzy system that is doing reinforcement learning. And this is a very challenging problem because basically we are trying to do explainable reinforcement learning. So that's a challenging research question, how to design a reinforcement learning method that is also explainable. Why is that difficult? Because there are many parameters in the system and you don't know how it really learns and why doing some given actions. Yes. So what triggers that given action? What value over what input triggers a given action? So the idea is, so Q-learning was basically, so deep Q-learning had the following idea: we approximate Q function with a neural network. In the fuzzy case, Takagi-Sugeno-Kang systems work very much like a neural network. So our big idea was to basically approximate the Q function with the TSK output, the output of the Takagi-Sugeno-Kang system on a parameter, on a state S and give an action A. Yes. So, okay, so Q of SA is basically the output of the Takagi-Sugeno system. So now we go back and see how this modifies our equations. Maximizing Q works the same way, except now Q of SA is the output of the Takagi-Sugeno system. Where is difference is here. Yes, this is gonna be a different output here, because here Q is the Takagi-Sugeno system, basically. Then we will have here the Takagi-Sugeno output derivative with respect to parameters of the system itself. So these are basically, everything is updated via Q-learning the usual way, except parameters of the Takagi-Sugeno system are updated via these equations. Yes, so this is reflected here. So I do the same update, target network. Yeah, I could have here target network. I forgot to put that. Minus or original one, and then basically here comes in the fact that this is a Takagi-Sugeno system. So this is a fuzzy system. That's the only place where the algorithm needs modification. So here are the steps again for target network. So with Q-learning TSK, we can use the same equation for Q. We can use the same target. Q of SA equations become this way, and we can again do updates, not every step, but a certain number of steps. Yes. Yes, so we update the steps, the parameters based on the equation for the TSK update here, this one. Yes, so we need this equation at this point using here the Y, basically, target function. Yes, but we don't do it every step. We do it after a certain number of steps. I don't know, that certain number of steps is typically not too big. So I could see implementation between 4 and 10 steps, basically. Update the network. Okay, there are variations there, but yeah, that's what worked for us. Okay, so here's a Q-learning with target network. One more explanation for that. So the initial state, we have the Q network. We predict the Q values with the TSK system here. Then we take the action A. We get in state ST plus 1. Yes. That will generate the target network. Yes. Then the target network is used for calculating the predicted Q values. Yes. And you use it to train your network. Yes. And then periodically you update your parameters so that the target network will be updated with the current network after a certain number of steps. So Q-learning has other issues. What do you do initially? That's basically the first question. And also how do I use what I already learned? So this is the experience replay method. So target network improves Q-learning, and experience replay also improves Q-learning. So experience replay is basically a set of states, actions, rewards, and next states that I have experienced before. Yes. And we can store them into a buffer called replay memory. Typical size 256, as you typically would take for anything that is a buffer. No, so basically we can use in this case mini batches from the buffer from the replay memory to calculate the target value. So how do you take this best action? If you have done no actions previously, yeah, then you basically go random. Take any action, record the rewards, put that into the memory. Yes. And after you have done enough exploration, so this is basically where your network is balancing exploration versus exploitation. So experience replay will allow you to explore the problem. Yes, and now if you accumulated enough experience, you will be able to get here a maximum, the best action. What was the best action in the given state? If it's in the memory, I will basically look through all the possible actions that I took and take the best one that was in the memory. If it's not in the memory, I have no choice. I'm just going to go random again, but improve my memory with adding those. Yes. All right. So that's another important concept in reinforcement learning. Next important architecture is the actor-critic environment. This is the simplest probably for doing reinforcement learning for TSK fuzzy systems, but it works reasonably well in many situations. So how does that work? Basically, we have an actor, which is so we have a policy. So actor-critic architectures looks for the best policy directly, doesn't look for best value, best Q necessarily, tries to get the best policy, which means I'm going to have an actor which acts according to a given policy. The critic evaluates the value function for that given policy, and basically then we can calculate the TD error, temporal difference error, between next policy minus previous policy. What if I change the policy a little bit? Is that better or no? That's TD error, temporal difference error. Change the policy, they change the action basically. You change just the next action to a different one. See whether you get better functions or better values or no. And if it's better, then you update your network in that direction. If it's worse, you update your network in the opposite direction. So basically you maximize your reward based on that. Yes. So the temporal difference is basically the reward plus the value based on next action minus the value based on previous action. Yes. So the policy that we have is pi next. The next state from S should be S prime. So I should go towards S prime. And now in our architecture, the actor is a TSK fuzzy system. So the actor is basically the Q value of the TSK. Q value approximated by the TSK fuzzy system. Yes. Then I change this system with a little bit, see what is the new output, and then I can update the parameters of the system to match the best possible output. Yes. So this system was used in many applications: gridwork, carpole, lunar lander. Yes. But here's what is interesting for you, probably. Team Hot Fuzzy, Alexander and Alejandro Herrera implemented an actor critic TSK fuzzy system and won in 2022 the XFC competition. Yeah, so also they published a paper, and we published a paper. Another one, another application that I wanted to cover today to go over it is an interesting one that was built by our Ben van Ostendorp and Eric Zender, together with my advisor contributions. Yes, so basically they built a reinforcement learning TSK fuzzy system for carpole environment using PyTorch and its automatic differentiation capability. Yes. So carpole environment. This is a well-known reinforcement learning problem. You want to learn how to balance the stick on the cart. Yes, so there is a cart and there is a pole on it, inverted pendulum system, and you can do two actions, left or right, with the same. So we don't have really different forces. You can apply a force to the small force to the right or small force to the left to catch it. Of course, here with this system, you can see you can apply this force and then balance it to reach equilibrium. Yeah, what happens here? Well, this one already is impossible to catch, so it would fall over. So how the system looked like in this situation, how they proposed it, was kind of like this. The input is then, so basically what happened is you want to have, so fuzzy rules work nicely, but you have, you need more structure to your network. So this is giving birth to so-called ANFIS DQN, adaptive fuzzy inference system. So this is a Takagi Sugeno system equipped with learning. So that's ANFIS. And DQN is the deep Q learning network. So this is the ANFIS DQN. So we have an ANFIS tail, yes, attached to a deep Q learning environment where you basically expand the variables. So you have basically the variables, the state, and or the angles or the angular velocities in this environment are fed to the network. But those are just 4 values, and it's really hard to predict what could be the ANFIS architecture to make that work. I mean, it's not hard, but not easy to learn with reinforcement learning. So to make the problem more, so to expand the number of parameters that you can work with, basically there is an expansion here, expansion layer. Basically, from the 4 inputs that you have, angle, angular velocity, velocity to the left, I don't know, there velocity and acceleration of the cart, angle of the pole, and angular velocity of the pole. So from those 4 inputs, you can generate a lot more intermediate inputs here. with the neural network, and you learn, basically train the parameters. Of course, here you lose interpretability, but the tail of the network is still interpretable at this point. Yes. So here, for the tail of the network, you use an ANFIS. Basically, you have a fuzzy rules that basically act out the policy based on the expanded variables that are basically latent variables. Then you have rule normalization. You could have first order parameters. So if there is basically just weights, not first order Takagi-Sugeno system. So if this is a zeroth order Takagi-Sugeno system, then the parameters will not be used. But if you have basically not a zeroth order, but first order parameters, then you can actually input that into the system. Okay, so that's the structure of the proposed system and how it behaves. Here's a comparison of ANFIS DQN versus standard DQN. So we were making we made sure to have the same number of parameters, same number of trainable parameters, same number of just the parameters, and all the other parts of the networks were the same, except one of them had an ANFIS, the other didn't have an ANFIS tail, but just a normal reinforcement normal output with similar number of parameters. So what we obtained is basically here blue is always the ANFIS and orange is the deep Q-learning standard conventional application. And for this example, we see that, so these two examples have actually a big advantage. They are a lot more stable than ANFIS. So ANFIS, the orange one, still goes up and down for the mean reward over different episodes. So basically, well, one more thing, what do you trace? How do you know your learning is happening? You can track the main reward. Don't track every, so when you're doing a reinforcement learning with TSK, tracking every step the reward, or with any reinforcement learning, tracking the reward every step is going to be very, very jittery. You want to do a mean of the rewards over different number of steps, and that's when you see how it trains. So basically, you train the network every step. You update the target network every once in a while, and you record the reward even more every once in a while, making average of the last couple of steps to make sure that it increases. So you have different, you can see that there are different parameters in the system, hyperparameters that you can think about. Anyway, so the blue one outperformed the orange one here and here, was outperformed in this situation. And here it's kind of the same. So what is the conclusion from here? That basically reinforcement learning with ANFIS or reinforcement learning have very similar performance, and they are at least, so reinforcement learning with TSK is at least as good as standard deep Q learning, if perhaps even sometimes you can see to perform actually better. Yes. What is the advantage? Why would you do ANFIS DQN? The ANFIS DQN advantage is in explainability. So you want to basically gain some insight of what's going on in these rules. However, it's hard to see here, so let me wait a minute. Anyone can explain what's happening here? So this is the rule base before training, and this is the rule base after training. On the horizontal line, we have a parameter that is computed based on all inputs together. So it's a latent variable, but it's good to use it for for that. So it's hard to see any distinction between these, but well, this is before training and this is after training. So what happened here? The rules are pretty uniformly distributed. Yes, so there is no basically any clear direction what you can observe. But here, output rule 0 is going left and output rule 1 is going to the right. So left is basically the blue ones, right is to the red ones. So here we can see that the blue ones and the red ones dominate each side of this. So we can see that basically if the latent variable is in this region, then most likely I need to go left. If the latent variable is in this region, I most likely need to go right. Of course, this is not a perfect information and not perfectly explainable system, but at least we gain some learning, some insight on what's going on in the system. Does it learn correctly? Do the rules begin to agglomerate around certain ways? Yes. So that's a lesson learned from this picture. Yes, so we can see that something is differentiating the rules when you go left from the rules that you go right, and that basically makes the system work. Yes. Conclusions here. Gradient-based methods balance the exploration versus exploitation trade-off in the exploitation direction. So if you compare what you have already seen in previous talks by Tim and Nick, was basically reinforcement learning. Well, not reinforcement. It was based on genetic algorithms. Genetic algorithms is fully in the exploration direction. They are randomized. Yes, randomized exploration. And while gradient-based methods are in the exploitation direction. And reinforcement learning is basically balancing those. Yes, so we allow some exploration, but also some exploitation. Yes, so we have been successful in deep learning, in reinforcement learning in fuzzy systems. Yes, basically this paper has been published in the Complex Engineering Journal, where we share invite special papers. Well, Tim has been also publishing the same issue. Yes. So here are our references. So these last results are in the Complex Engineering Systems Journal. Then other references you can see here. Yes. Thank you very much. That's all. And I'm going to be answering questions if you have questions.
Thanks, Barnabas. Since
Thank you.
I'm the only one here, I'll go ahead and ask a question that I assume most student competitors will have, which is, do you have any advice for bridging the gap between what you've shown in theory and obviously you've had students under your mentorship implement this for the competition, besides reading the paper? Is there any advice you would give to those students that may want to try reinforcement learning for their agent in Kessler?
So an advice for those students who want to try reinforcement learning is to start with a simple architecture. Typically, actor-critic is simple enough to be able to learn. Yes, and start with simple scenarios or random scenarios. Also, don't learn on specific scenarios, because teams that randomizing every step the scenario worked better. However, that gives a huge variability to the reward that you get. So you need to look not only reward on last 10 epochs, but rewards the last 40 epochs for seeing actually some improvement that is going on or so. Another advice is you need to learn how to be patient. This is not gonna be fast. So reinforcement learning is notoriously the slowest method of learning, but it can discover behaviors that as human you wouldn't actually do. So reinforcement learning is able to train for situations that were not foreseen by you. So it's gonna basically have a rule for a crazy action that it could take that basically saves the ship in some situation. So that's possible. Another thing is a good combination between exploration and exploitation. Here also matters how many steps you basically do exploit the environment, play it just random with the fuzzy system in the current state. When you update, that's also, yes. But if you are running out of time, then don't do this. You need the time to train the network. So allocate, well, no, I'm wrong. Sorry, I have to rephrase my advice. Allocate some time for really training the network. So you need to have the network ready to train before well before the competition in order to be able to train it correctly. Because first couple of trainings will not work. Then after you get the reward shaped in a way that it makes sense, then you have to let it run extensively until it really shows training. Yes. But it's really fun to see when your agent is learning some behavior that you wouldn't expect. So that's really nice, though.
Yeah, no, that's one of the most fun parts, I think, is finding interesting things that it learns to do based on rewards.
Mm-hmm.
Which reward shaping is a whole topic that we get into a little bit in the gradient free talk as well.
Mm-hmm.
But yeah, that's a big aspect. So sounds like the takeaway is don't procrastinate as usual.
Yeah.
Well, thanks again for the wonderful talk, Barnabas. I'm sure there will be plenty of student competitors with questions about how to implement some of this stuff. We will definitely be using your previous student team's work, not as a template, but as a guide for maybe how to implement some of the methods. So thanks for your time in giving the talk, and especially one of the points of the competition is for students to learn how to do this and to do research in it. So I'm glad that your students were able to do that. Yeah.
Thank you very much for inviting me, and thanks for the opportunity. So to all competitors, please feel free to share my address, email, and stuff like that, so that they can reach out for questions. Yes.
Will do.
Digipen's teams will reach out for questions for sure, but other teams, please, you are welcome to ask questions if you decide to use some of the ideas in the reinforcement learning direction.
Yeah. I'll share that info with everyone. Thanks again, Barnabas.
Thank you, Tim. Bye.
Bye. Thanks. All right. Well, that concludes our seminar on reinforcement learning in fuzzy systems. As usual, it'll be uploaded to YouTube soon. And yeah, thanks again. Bye, everybody.